difference between x plus x, x times x. So let's start with x plus x. X plus x. So when we're adding, I like to think of the x creature. I'm holding a little x creature in my hand. Now picture your x creature. He might be fuzzy. Mine has a tail, right? He's in my hand. I add another little x creature to it. How many x creatures do I have? Two x's, right? So when you're adding x's, picture kind of physically holding them, or if you're subtracting x's, they're leaving your hand. Okay, so you physically can see them. Now what's going on when I multiply x times x? I have factors of x now. How many factors of x do I have? So how do I write that? X squared. We don't want to mix up x plus x and x times x. They're different. X plus x says how many? I have two x's. This says how many factors. It's asking something different. How many factors of x? I have two factors of x squared. All right, so we want to keep that straight. If this is an issue, maybe even star it, because you want to keep that straight. So now when we look at the rest of them, I think we're okay with expanding x to the third power. How does that expand? X to the third power, what is that?
That would be x and x. Right next to it.
Well, yeah, first I'm going both ways. So if you have x to the third power, what does that mean? 3 factors of x. Here they are. If I have 3 factors of x, what's another way to write that? X cubed or x to the third power. So they go together, they mean the same thing. They both mean 3 factors of x. Okay. So let's see, when we multiply, we get a power. How many factors of x? That's what multiplying tells us. All right, now we're going to try this little job here. We're going to multiply exponents. And let's think about what we're doing. So I've got an x squared times an x fifth. Well, x squared, what is it? That's 2 factors of x, right? Isn't that what x squared means? And then I'm multiplying that by 5 factors of x. Hopefully I wrote down the right number here. So how many factors of x do I have? I have 7 factors of x. How do I write 7 factors of x? I mean, this is one way. What's another way to write 7 factors of x with a lot less writing? X to the 7th power. So let's look at what we did here. When we multiply powers with the same base, we're basically asking, how many factors do you have? You have 2 factors here, you have 5 factors here. How many factors are there together? 7. So if I have, let's try the y. Y to the 10 times y to the 20. Well, how many factors of y do I have? How many factors? Y to the 30? Y to the 30. Because here's 10 factors of y. I've got another 20 factors of y. There's 30 factors of y. I see that. I mean, who sees that? What's a question? What's a question? I don't know. See that. Okay, good. So let's see if we can come up with kind of a rule here. Okay? We're remembering that multiplying powers with the same base is the same as asking how many factors we have altogether. So when we multiply powers with the same base, what are essentially we doing with these exponents? We're adding them. So in this blank, you're going to write add. Multiplying powers with the same base is adding exponents because we're asking how many factors do we have altogether. 10 factors plus 20 factors is going to give me 30 factors. Okay? We're following? Who's following? I'm following. So, we're not following. Just kind of, and I want you to ask. If it's too fast, slow me down. Because getting this is so essential to a lot about what we're going to be doing. Not only, this class and the next couple of classes, but even later in the year. Really getting this. Let's look at this division. So I've got a division here, x to the 5th over x to the 3rd. Oh my goodness. Let us go ahead and expand that. So I've got 5 factors of x on top, and I've got 3 factors of x on the bottom. Now, an important thing to know to kind of see this is to understand what x divided by x is. As long as x isn't 0, what is x divided by x? Now, one person sees it. I want some more people to kind of think about it. If you don't see it yet, I know you got it. I know you got it. Think about 5 over 5. What's 5 over 5? 1. What's 10 over 10?
1.
So tell me, what is x over x? 1. So anything divided by itself, as long as that anything is a 0, is going to give me 1. So let's look over here. See this x over x? What does x over x equal?
1.
Here's another x over x. What's x over x equal? 1. What's x over x equal? What's 1 times 1 times 1? 1. How many factors of x are left over here?
2.
So I write 2 factors of x as x squared. So how do we get there? I had x to the 5th over x to the 3rd. There were 3 factors of x in common. How many factors were left? Okay, I like that sound. One person it turned on a little bit, right? Yeah, yes ma'am. You're subtracting. When we divide powers with the same base, we subtract the exponents, mostly because we can cancel out that minimum number, right? It's going to be the same number on top and the bottom. So they're going to go away, and I'm just going to have those 2 left. So when we divide powers with the same base, we subtract. And the reason I'm kind of giving you the examples is because I could have just presented you with rules. When you multiply, you add the exponents. When you divide, you subtract. I don't know if you're like me, but I know if you had just presented me with rules, they would go in one ear out the other. I wouldn't remember it for anything. But if you know how to recreate, you got this. Okay? So the actual how we got there is important. And let's look at this example. I've got x squared and I'm raising it to a power. Look at that. X squared to the 3rd power. Let's expand it. Because I think it's a little hard to see. That means I have 3 factors of x squared. Isn't that what that means? If you take x squared, that's my base. And I have 3 factors of it. Do we agree? Okay. So now we're answering the question. That's a multiply problem. How many factors of x do I have? Got 2 factors here. 2 factors here. Yep. How many? 6 factors of x. So this x squared raised to the 3rd power was x to the 6th. Oh, what do we do? What do we do with those little powers? We see the pattern. Do we add them? What do we do with them? We multiply them. So here's a power raised to a power. When you do that, you are going to multiply. So it's confusing already, right? Sometimes we're adding them, sometimes we're subtracting them, sometimes we're multiplying them. Instead of memorizing, I want you to expand. Oh, expand it until it's in your brain. Expand it out until you can see it. That I don't want you guessing. I don't want you to try to think back. What was it? I want you to expand it out if you can't remember those rules. And then you don't have to remember. It'll go in. It'll just be there. Trust me. Oh no. Look at this one. So in parentheses, look at my base. X cubed y 4. And I'm raising that base to the 3rd power. Now that's frightening. Oh, let's expand it, right? We can always do that. So here's my base. How many factors of this do I have? I have 3 of them. Right? Go like this, if you're right. Okay, good. All right. Now what I'm going to do is, this is multiplying. I can multiply in any order I like, says the commutative property. So I'm going to gather my x's together, and I'm going to gather my y's together. With me so far? I just kind of shuffled them around a little bit, using power multiplication. How many factors of x do I have? I have x to the 3rd times x to the 3rd times x to the 3rd. How many factors of x do I have? 9. And now I've got y to the 4th times y to the 4th times y to the 4th. How many factors of y? 12 of them. Let's look a little closer here. This x to the 3rd, y to the 4th to the 3rd power became x to the 9, y to the 12. So we kind of see what we did. What we did here? Yeah, it was like we just took this x to the 3rd and we raised it to the 3rd power. And we took this y to the 4th, we raised it to defined to be of the distributive property. It's not the distributive property, but it's like it. So we're raising 3 to the third power, we're raising 4 to the third power. You apply the power to all the factors inside. So when raising a product to a power, each factor is raised to that power. All right, we're getting there. One more I want to look at. Now I've got a fraction raised to a power. Well, we've done this already. This is my base, right? So can I just take that base, that factor, 3 times? Right? Isn't that 2 to the third power? All right, let's multiply it. So remember how I multiply? Numerators, 2 times 2 times 2. How many factors of 2 are there? 3 factors of 2, that's how I write that. How many factors of 3 on the bottom? So let's see what I got here. This 2/3 raised to the third power. That was 2 to the third over 3 to the third. So basically, what would we do? What would we do there? Exactly. So we raised the numerator to the power 3, we raised the denominator to the power 3. So, because I have 3 factors of 3.
Oh.
Right? Expand it out and you can see it. Then it's not magic anymore. I don't want this to be magic. I want you to know where it came from. But that way if you forget, you can just rediscover it. It's always nice when you can just rediscover it. So let's put some words to this. When we raise a fraction to a power, what are we doing? We raise both the numerator and denominator to that power. Okay? And those of you that said distributive power before, it's similar to when we had a product, right? We applied that power. Same kind of thing. Now we're doing quotients, but we're applying that power to it. So when we raise a fraction to a power, we raise both the numerator and the denominator to that power. Let's see if we can kind of maybe put it together just a little bit. So let's look at some examples here. X to the third times x to the seventh. Remember, all I'm asking is how many factors of x do I have? How many factors of x do I have? X to the third, x to the seventh. 10. So x to the 10. Don't take 10, right? X to the 10. I've got 10 factors of x. Now how about this one? In my numerator, there's 10 factors of x. In my denominator, there's 8. How many am I going to be able to kind of cancel out? Well, I'm going to cancel out 8 of them. So how many are going to be left? X squared, right? 2 powers of x. Think about x to the 4th. I'm repeating that as factors 5 times. X to the 4th times x to the 4th times x to the 4th, right? 5 times I'm doing that. So how many factors am I going to have? 20 of them. 20 factors of x. There's my multiply. Now I've got a little bit more complex. There's a product in there as my base. So x squared y to the 4th. That's repeated as a factor 6 times. So how many factors of x will I have? And how many factors of y will I have? Well, how many factors of x? X squared 6 times. 12. Right? Because that's x squared, times x squared, 2, 4, 6, 8, 10. I've got 12 factors. Now I've got y to the 4th repeating 6 times. So how many factors of y are there? 24. So that's like raising 2 to the 6th power and 4 to the 6th power. How about x over y to the 5th power? What's another way I could write that where I don't need those parentheses anymore? X to the 5th over y to the 5th, right? The 5 goes with the numerator, and the 5 goes with the denominator. So these are called the laws of exponents. Here they are in a nutshell. If I had just given you this, it would be really confusing. I think it's important to see the examples. You might want to write examples next to it. So if you have raised to a power, it's the same base you add the exponents. Why don't we just put a simple example? X squared times x cubed, that's x to the 5th. 5 factors of x. If you're dividing x10 over x7, you subtract those exponents because I'll cancel out 7 of them. later in the year. So hopefully when we get to it, we'll think back to this and we'll remember the rules. But we actually need it for what we're doing today. We need to understand a good bit of this. Do we have questions on this? Are we able to follow it a little bit? Let's say, well, you know what, I can try to follow this. It's a little confusing, but I can follow it. We'll get there. Do you think you could recreate, if you forget the rules, because I know I wouldn't remember them. If you were to give me a test on the rules the day that I learned this, I would not remember a single rule. But I think I can remember how to recreate it. And that's good enough. So that's where we're going with this for now. What's a perfect cube? We know what a perfect square is. What's a perfect cube? What do you think, Lynn?
It's just a little square except step 3.
All right, so this, I made my cube definition to look at my square definition. Remember this cube root is an integer. You might want to say it's an integer that has 3 equal factors. An integer with 3 equal factors. So what's an example of a perfect cube? 12? Should I have?
Oh, wait, no.
She's working it.
Yeah, 9, no.
Does 9 have an integer that I can do 3 factors of it? 27. Now how'd you get to 27? 3 times 3 times 3 equals 27. So does it have 3 equal factors? What else? 8 has 2, right? 2 times 2 times 2. It has 3 equal factors. That's a perfect cube. So let's write the first 10 perfect cubes. These are a little bit less well known, right? And how do we get there? Same thing. We're going to do 1 cubed, 2 cubed, 3 cubed. All right, we're going to just create the list. Same method as we did with our perfect square list, except now we're cubing these numbers here. So let's see, what are they? 1. 2 cubed, you told me is 8. 3 cubed, you told me is 27. That's 4 cubed. 4 times 4 times 4, 16 times 4. What else we got here? 5 times 5 times 5. 6 times 6 times 6. What is it? It is. Thank you. He can do this stuff in his head. He's kind of really good guy. Did I do these right? Did I do them right? Okay, good. He's checking on me. He can do this stuff in his head. He's kind of amazing. It is amazing. Now, if you're not as amazing as him, I'm sure I'm not, you have a calculator too. You're not getting them today, but you'll have them eventually. So if you want to recreate this list, type in 6 to the 3rd power, you'll get what it is.
Or 6 and 6 and 6.
If you can do it, he can do that in his head. The mere mortal, sometimes that's a little hard. So if you want to recreate it quickly until we have it more familiar, hopefully, I'm going to hope that at least this much you get right away, perfect cube. And the other ones we're working towards. We're working towards them. All right, so let's see. What's a cube root of a number? Just like with the square root, the inverse or the opposite of cubing a number, the number that when taken as a factor 3 times gives us what we started with. So what's the cube root of 27? 3. Right. So let's look at some examples. Now when we write it now, it's using that same little symbol that we were using with square root, except we put a 3 here to say I don't want a square root. I don't want the integer that when taken twice gives me the number. I want the number that when taken 3 times gives me the number. So what is that cube root of 8? And again, you can look up here. Here's 8, 1, 2. Cube root of 27. 3. Cube root 125. Uh-oh. Cube root x to the 3rd power. X, how'd you get that? 3 minus 3. Why are we doing 3 minus 3? 3 minus 3 is 0. We have to get x out of that. What times what gives me x cubed? X times x times x. Let's look at this guy. Now this one, I'm going to break it apart. We look first at the cube root of 8. What's the cube root of 8? Cube root of x to the 6. Let's think about that a little bit. Now I need 3 factors that equals x to the 6. So x to the what?
To the 2nd power.
Right? You add all these. Does it work? Because x squared times x squared times x squared. How many factors of x do I have? 6. Because I'm answering the question, how many factors of x do I have? How many factors do I have here? How many factors do I have here? How many factors do I have here? So how many factors of x do I have? 6. Because that's what this tells me. How many factors do I have? No. Is adding the same as multiplying? No. If you were adding these, think of the x squared creature. Maybe it's got 20 ears and fangs. So you're holding an x squared creature. I give you another x squared creature. How many do you have? I give you another one. You have 3 of them. So this is counting how many x squared creatures do I have. This is saying how many factors of x. It's different and it's subtle. And I know she's working on it. You got to really think about it. You got to really think about it. I didn't say it was easy. And I like that she's really working it. Good. You should ask me this more often. I'll do it again. Because we really have to get that in there. All right. Okay. Let's try a different one. What is the cube root of x to the 9th? How do we get that? Because x third times x third. What's the cube root of x to the 27th? What is it? How are you getting that? X to the 9, you're right. What do you do? Cancel it? What am I canceling? Say one more time. Well, I'm saying it equals, right? So the cube root of x to the 27 is x to the 9. Because x to the 9 times x to the 9 times x to the 9. Do we see any sort of pattern? What? We divide. So if it's divisible by 3, it's a perfect cube. If it was divisible by 2, wasn't it a perfect square? So if your exponent is divisible by the kind of root you're taking, it's a perfect root. Yeah. Yes, yes it is. We divide that. We divide that. Let's try this fourth root. Not even anything on our radar yet. What's the fourth root of x to the 16? You know how easy that is? So we can tell perfect squares, perfect cubes, perfect fourth powers if they're x's. In a way, the variables are actually easier. Once you get used to them, they're easier. So don't find me on variables. No, they are. She's giving me the face. No, they are. Look, we don't even know what a fourth root is, and you told me the fourth root of x to the 16. Oh, okay, on that note, when we get back from lunch, who's brought a lot of sugary stuff for lunch? Anybody? Let's get back to business here. Y'all told me you didn't have too much sugar for lunch, so you're all ready. You're all ready. So let's just review some stuff. So this symbol here, this little guy here, we've been calling it square root. There's nothing wrong with calling it square root. But its real name is radical. It's called a radical. Because sometimes it's a square root, sometimes it's a cube root, fourth root, fifth root. So we're just using this global term radical to mean this kind of a symbol. And the way it works is you have this thing inside, and there's a little number out here. And the little number tells you what kind of root you want. The y, this number inside, we call that a radicand. So the inside is the radicand. And by default, so if there is no little number here, we assume it means 2. So if we mean 3, then we better put that in there. But if we don't put a number in there, it means 2. You could put a 2 in here. There's nothing wrong with that if you wanted to. And it just means take the square root, take the cube root, take the fourth root. So that's what we mean, just for terminology points. So let's see where we are now. Okay, so we're kind of here in the middle of page 1. And we're learning how to simplify radicals. Just like fractions, right? We can simplify fractions. In fact, we have to. That's kind of the rule. If you have a fraction, you have to simplify it. Radicals, these square roots, cube roots, same way. If they can be simplified, you have to simplify them. And we have 3 rules that we're going to follow for simplification. Excuse me. hiding in the radicand. Remember what the radicand is? It's like this, the number inside. It can't have any perfect square factors. Part of simplification is, if I have some perfect square factors, let me take their perfect square. I'm going to take them out and take their perfect square. So that the only thing inside is something I cannot take a perfect square of, or a perfect cube, or whatever you're working with. You can't have fractions in a radicand. So a simplified radical can't be this, because there's a fraction inside. So we have to simplify that and fix it. We'll see how. You also can't have a radical in the denominator. So something like this is not simplest form. We can't have something like that. So we're going to have to learn these three things. Today I want to concentrate on the first one. How do we find if there are perfect squares inside the radicand that can come out? So let's look at that here. There are two properties we're going to be using. Two properties of radicals. And they're similar to the properties that we looked at earlier for exponents, because radicals in a way are exponents. In fact, they are, but you'll learn more about that in Algebra 2. So anyway, here's the square root of AB. That is the same as taking the square root of A times the square root of B. So if I have the square root of 2 times 3, that's the same as the square root of 2 times the square root of 3. It works the other way. If you see the square root of 4 times the square root of 2, that's the same as the square root of 4 times 2, square root of 8. So you pull them apart and you can put them back together. With a fraction, you can do the same thing. So if you do have a fraction under a radical, you can tear them apart. So we were looking at the square root of 2/3. That's the same as square root of 2 over the square root of 3. And I don't know if that reminds you of any of our exponent type stuff that we looked at. Remember we had x squared to, let's say, the 5th power? What was that? It's that same kind of idea. It's the same idea that if you're taking the radical of the whole thing, it's the same as the radical of the numerator over the radical of the denominator. Alright, so we're going to be using these rules. So let's look at what we got here. Okay, so I can't have any perfect squares in here, perfect square factors, other than 1. So the first thing I'm going to do before I even read this is remember that list of perfect squares that we made? Remember that? Let's make a list. Here are these problems. So maybe put it along the bottom, so you can see it along the bottom. So what's the perfect square list? 1, 4, 9, yep, 25, 36, 49, 64, maybe you want to put stuff at 100, but you can make it longer if you need to. Having that perfect square list staring you straight in the face helps you know, well, what am I looking for? I'm looking to see if any of these numbers are a factor of 32. And I want the biggest factor, perfect square factor of 32. So one way to do that is to say, well, 32, where is that on my list? It's over here someplace, right? 32. So I'm going to start looking left of it. Is 25 a factor of 32? 25 times something, does that give me 32? No. So that doesn't help me. Is 16 a factor of 32? It is. 16 times what is 32? 16 times 2. So I'm going to rewrite this as a product. Isn't 32 the same as 16 times 2? And it's square root 32, so it's going to be square root of 16 times 2. All I did was I put this in factor form. Put the perfect square first. Okay? Now I'm going to take that rule I just told you about. So if I'm multiplying stuff inside a radical, I can make a radical of each thing. So now the square root of 16 times 2 is the square root of 16 times the square root of 2. What's the square root of 16? 4. And then I have the square root of 2 because it's 2 a perfect square. No. Does it have any perfect square factors other than 1? That's about as low as I can get. So the simplified form of the square root of 32 is 4 square root 2. Yeah? Let's see if we can do a different one. Just kind of think off the top of my head. I don't know. I might hurt myself, but let's see. Let's just try another one. I don't have too many examples here. The square root of 20. Are there any perfect square factors of 20? Well, let's look. Where's 20 on here? 20's over here someplace. Is 16 a factor of 20? 9 a factor of What's the square root of 4? 2. Square root of 5. Are there any perfect squares hiding in there? No. So the square root of 20 is 2 square root of 5. See what I'm doing here? A little bit? So I'm looking for any perfect squares. I'm taking them out. Taking out the perfect squares so that all I have left are the things that I can't take a perfect square. Let's look at this guy here. Now this one has variables. At first variables are going to look hard, but after a while variables become easier than the numbers. So let's see what we got here. I've got the square root of 9x cubed. I have a rule that says if you have a product, you can break them apart, so let's do that. Break apart the number and break apart the variable. Oh, I know what the square root of 9 is. What's the square root of 9? Where'd you go? What's the square root of 9? 3. Is this a perfect square? When I take a square, is there x to the something times x to the something that gives me x cubed? With an integer exponent, there isn't. So we're kind of doing the same idea here. I look for the biggest number perfect square. I want the biggest variable perfect square. And it's the same for all of them. What you're basically going to do is say, well, x cubed isn't a perfect square, but you know what it is? X squared, one less than that. And if I want this to equal x cubed, x squared times x, is that the same as x cubed? How many factors do I have here? 2 factors, another factor. That's 3 factors of x. That's this, right? Now watch me split that part apart. 3 times square root of x squared times the square root of x. Okay, well there's the 3. What's the square root of x squared? What times what is x squared? X. Right? And I can't take the square root of x. That's one of those things. It's an odd number exponent. I can't, it's not a perfect square. So this one becomes 3x square root x. So at first, the variables are going to trip you up. But believe me, they're not as hard as you think once you kind of see the pattern that we're doing with them. And these are you tries, but let's just do them together and see if we can figure this out. So I don't have to worry about variables with this one. But the square root of 24. So 24, so it's less than 25. So I'm going to start here. The 16, is 16 a factor of 24? 16 times something 24? No. 9, is that a factor of 24? No. 4, is that a factor of 24? Yes. Right, 4 times what? So the square root of 24 is the same as the square root of 4 times 6. Put your square root first. Your perfect square comes first. Then break them apart, because we have that rule. What's the square root of 4? 2. The square root of 6. Now I always check this one. I'm like, gee, can I take the square root of 6? Are there any perfect squares in there? Let's think of the factors of 6. Well, 1 we're not counting. 2, 3, 6. That's it, right? Are any of those perfect squares? No, they're not. So this is as low as I can go. What you think? Have I lost anybody? We got awfully quiet. Awfully quiet. All right, let's look at this guy. So now it's a product. So let me break it apart. I'll put the numbers in one, and I'll put the variable in the other. And let's see, what's the square root of 25? What's the square root of x squared? Oh, so these were 2 perfect squares. So this is a perfect square, because 5x times 5x is 25x squared. So that one happened to be a perfect square. What if I would have had 25x squared y to the 4th? What do I do if I have more than one variable? What do you think I do? Okay. Okay, so then we can start taking roots. So square root of 25 is 5. Remember to take it out of the root. Some people like to say that's square root 5. That doesn't make sense. Right? Right, because x times x is x squared. Good. So we just, however many variables they give you, just split them apart and work them. Work them each separately to get what you need. Okay. Say it again? Well, am I taking the square root now. Once I take it out of the radical, am I asking for the square root? So she wants to keep going. Well, I can take the square root of y squared, right? You can, except am I asking for a square root now? It's like 5 came out. Do I want the square root of 5? No. What's the square root of y to the 4th? It's y squared. So yeah, once you've taken the root, you're done. You can stop. I think that's what you're asking, right? Can I take this root too? Yeah. It's not a square root anymore. It's just plain ordinary y squared. So I don't take its root unless I'm told to. If this was the square root, or if it was this, I don't want to blow your minds too much. Then I would agree with you. Because that would be the square root of y squared, which is y. But once you take the root out, it's not under a radical anymore. Once you find what its square root is, you just take it out. Okay, I don't want to do that yet. I'm going to look at the U-tries on the back. And let's try some of these together because these are a little bit tough at first. So we're on the back. Do you have your list of perfect squares with you? I don't see them. Should we put them back up? One, two. And you'll get good at this. Put a perfect square list on the back of that paper. I hope I'm not leaving anything out. Sometimes I do. Okay. Got your perfect square list going? Write them up. And let's try the square root of 3. Right. You kind of did this one, but let's see if we can remember what we did. What's the biggest perfect square factor hiding there in 10? What is it? 4 and 4. So that's going to be the square root of 4 times 5. I can break that apart. I know what the square root of 4 is. That's a perfect square. And I check here. 5. I don't have any more perfect squares hiding. So 2 square root of 5. Now the square root of 72. I'm going to try something a little different here. Sometimes we don't always see it. We don't always see the biggest perfect square. We see a perfect square. For example, when I look at the square root of 72, I saw 9 times 8. Isn't 9 a perfect square? So if I do this, oh wait, that's 9 times 8. I'm correct, right? Yeah. And so I'm going to break it apart. And let's see, square root of 9 is 3 times the square root of 8. And if you gave me this, I'd mark you wrong. And I don't see an error. What's the problem with this one? Claire, what's the problem here? Yeah, because is there any perfect square factors hiding in 8? What are the factors of 8? 1, 2, 4, 8. 4. So what I need to do is I gotta keep going. Do you ever reduce a fraction? You didn't quite reduce it enough? You I don't know, 8/12ths? And you went down to 4/6, you're like, no, I can keep going. You didn't pick the biggest common factor? It happens. So you just keep going. My 3, now this is multiplied. We don't see any kind of operator, it's a multiply. So it's 3 times the square root of 4 times 2, which is 3 times the square root of 4 times the square root of 2. And that is 3 times, what's the square root of 4? 2 times the square root of 2. Now, these are both outside the radical. I can multiply them. What's 3 times 2? 6. 6 square root 2. Now, if you had done this one, I'm going to say properly, maybe you saw the biggest perfect square. The biggest perfect square is actually 36, because 72 is 36 times 2. And now, we don't always see that right away. So, I can see from here that it's 6 radical 2. But as long as I check, when you kind of get it lower and say, oh wait, let me look in here, are there any more perfect squares that I might have missed? And just keep going. Kind of like when you're reducing a fraction and you kind of have to keep going a little bit. Yes or no? Nothing. Okay. Because I think you're stunned a little bit. You might just, I'm stunned. Where'd this come from? It was going along just fine, and now this is like, you're taking a new language, and what just happened? I think these are kind of fun. Once you get used to them, they actually are a little bit fun. Let's try this one. Fun! All right. So next one, I got a variable. I've got a variable with me. So let's see. apart to the number and to the variable. Let's just tear them apart a little bit. So let's work on this one now. Square root 32. I have to find if there is a perfect square hiding in here. Do I have a perfect square factor? 16. There we go. So let's break that up into 16 times 2. Now let's look at x to the 5th. This is not a perfect square because it's an odd number exponent. What's the biggest perfect square? Meaning, what's the biggest exponent that's a factor of this? Hint, it's always one less than what you got. 4. Because what is x to the 5th? It's x to the 4th times x. You're going to do the same trick for any odd numbered one. You take one less here times x, because this is still 5 factors of x. All right, let's go into the breaking it apart stage. That's the square root of 16. That's the square root of 2. That's the square root of x to the 4th. Phew, that's a lot of stuff going on. Well, let's see what we can do. Well, I know what the square root of 16 is. What's that? And if you don't know, look here. Right here, 16, you can just count over. 1, 2, 3, 4. Okay, so square root of 16 is 4. Square root of 2 has no other perfect squares in there, right? 1, 2, nothing I can do with it. What's the square root of x to the 4th? X to the 2nd power. And the square root of x, that's again an odd number. It's not a perfect square. I gotta leave it like that. Maybe somewhere. Now, the convention is we always put the stuff outside the radical first. So move those together, because we're just multiplying all this. Multiplying says you can multiply in any order. So move the stuff outside the radical first. Then I've got a square root 2 times the square root x. Now I've got a rule. If you're multiplying separately, they can be put together. And so look at that. The simplified form of radical 32x to the 5th is 4x squared radical 2x. Wow. That's kind of mind-blowing, isn't it? We've been keeping this from you all this time. We're letting you in on a secret. One other example I kind of want you to look at. It's not on here. If I have the square root of, I'm trying to think of a good one, 10 times the square root of 4. And I want this simplified. I'm giving you a product here. How would I do that? Any ideas what I could do with that? Well, I'll tell you. My advice is let's put it back together and see what we have all together. So what's the rule? I can put them all under 1, which is the square root of 40, and then you can work from here. Now this is kind of probably a bad example because we want to get back to here. The perfect square hiding in here is the 4. So this is the square root of 4 times the square root of 10 is 2 square root of 10. So I guess what I'm trying to tell you is if you're given one where they're multiplied apart, stick them back together and just start from fresh. I think that's the easiest way to work with those. What else? What else should we think about with the radicals? Square root of, let's try a different one. 200 x to the 3rd power. Let's try that. So what's my first step, Mary? Well, let's first just take them apart, right? And then I look for the biggest perfect square. So what's the biggest perfect, we need to go, the biggest perfect square hiding in 200? 100. So that's 100 times 2. Now what about this? This is not a perfect square. X squared times x. You always take one less, because that's going to be a perfect square. The biggest one. All right. Square root 100 times square root 2 times square root x squared times x. What's the square root of 100? 10. Can I do anything with the square root of 2? Square root of x squared? Can I do anything with the square root of x? Okay. Now we just have a little house cleaning here. So how do I rearrange this into my final answer? Yeah.
Take x times 2x square root 2x.
Yeah. So you take the ones outside, and they go in front. So my 10x gets moved in front. The radical 2, radical x, multiply them together, they're both under the radical. Okay? So a lot of rules here. A lot of rules. So